Hello students, let's do lesson 9, esterification and combustion. We want to talk about esterification and in particular today combustion. We want to predict the products and write and interpret balanced equations. And we want to predict the ester formed from an alcohol and an organic acid. Okay, now we've talked about esterification before, so we'll just quickly review that. Alcohol plus carboxylic acid makes ester and water. And remember, the carboxylic acid becomes the parent and the alcohol becomes the branch. So here it is again. H and OH are removed and the alcohol moves over and now we have an ester. Now you've seen this a couple of times already. It could look like this too. We could have an aromatic molecule that has a carboxylic acid attached, benzoic acid. So we go through the same process and there, now I have another ester, propyl benzoate, 1, 2, 3, and I've got water. Now I've shown you ester reactions a number of times. Now you could come across questions like this. Name and predict the reactants that would produce this compound. Okay. So you got CH3, CH2, COO, CH3. Now, first of all, we should recognize that as soon as we see the COO, we should go, oh, there, that's an ester. That's a C double bonded to O, single bonded to O. That's an ester. We should recognize that this is the branch and that this is the parent. Okay, now this parent was 3 carbons long. That's prop. Now this was formerly a carboxylic acid, a propanoic acid. Alright, this is 1 carbon long. That's our branch. It's a meth because it's 1 carbon. It was an alcohol, so it's methanol. So this molecule here, CH3, CH2, COO, CH3, was formed by the reaction of this carboxylic acid plus this alcohol. We made this ester and we made water. So this plus this makes this and this. And this was propanoic acid originally, and this was methanol. Okay, perfect. Let's talk about combustion. So complete combustion is when you have lots and lots of oxygen. And like you learn in grade 11, we produce CO2 and H2O in a combustion reaction. So let's say I have 2 octane molecules and 25 oxygens. I'll make 16 CO2s and 18 waters. Okay? When we have lots of oxygen, we make CO2 gas. Now what if we have less oxygen? What if we have what's called incomplete combustion because we have a limited oxygen supply? Well, as you can see here, this produces carbon monoxide, not carbon dioxide. I didn't have 25 oxygens, I only had 17, and that changed the formation of my product. It's now carbon monoxide, this poisonous gas, instead of carbon dioxide. And if I have really poor oxygen supply, I'll actually make my carbon, there's not even an O on there because I don't have enough oxygens. Okay, so when I have lots of oxygen, like 25 oxygens here versus 17 or 9, I make CO2, CO, or C. Now, evidence from experiments indicates that all 3 types occur simultaneously when an organic compound is burned, although not in equal amounts. The ratio of the 3 reactions depends on the amount of oxygen present. So when you burn something, let's say you're burning some wood in a fireplace or on a campfire, it's actually giving off CO2 and CO and carbon. Okay? And if you got lots of oxygen, it's going to be more CO2 than CO. But just think about that fire. When you're burning that fire, when the leftover ash there's black stuff in it. That's carbon. And there was some poisonous gases being given off, which is why we have fireplaces in our houses to get rid of the smoke and the carbon monoxide. And then there's carbon dioxide given off as well. So all three actually happen. We tend to think that everything's nice and neat and just one reaction happens, but actually all of those reactions are happening when we burn. Okay, and sometimes these reactions are balanced using fractions. Oh, I don't have a picture there. So imagine that sometimes we'll have like a 25/2. And you'll see that when we get to the next unit. Anyway, okay, I wanted to make sure you understood what combustion looks like. So we write reactions on paper like this. CH4 plus 2O2 makes CO2 and H2O. And I think sometimes students think the reactants and the products are both present at the same time, because on paper we see everything at the same time. But it's actually not like this. Notice here I've got methane and my two oxygens, and I can't see CO2 and I can't see water anywhere. That's because they're not there yet. Now, when burning happens, all of these bonds snap. And everything gets tossed around. All these atoms get tossed around or get jumbled up. So watch. I snap the bonds, they disappear, and boom, now everything's in chaos. And now everybody's looking for a dance partner. They got to bond with somebody here. So I then go and form these new products, these new compounds. And look, I've got C with two O's, that's CO2. And I've got two water molecules, HOH or H2O. Notice this is gone and this is gone. And that's what reactions really look like. It's hard to do on paper, but I start with these two reactants. They get all jumbled up, and then they make these two products. Okay? Alright. Now there are some reactions you'll see later on in the acid-base equilibrium unit that are actually everything's present at the same time. But a reaction like combustion, we start with two things and we end up with two different things, and they don't exist at the same time. Okay, let's talk about the automobile here. So what does this look like inside your car? Okay, so now we're going to take gasoline and put it in our car, but I'm going to just simplify this. I just want to pretend the gasoline is methane, just because it's easier for me to do a diagram. But the same principle will apply. So here's my methane molecule, which is supposed to be our octane. Here's my two oxygens. So you pull up to a gas station, and there's the gas tank right there. You put some gas in the car. When you turn the car on, the gas gets shot up into the engine, or pumped into the engine. So there's my gas molecule, my methane, goes up into the engine. Turn your engine on, and oxygen goes into the engine as well. You got to have oxygen to burn fuel. So that oxygen gets sucked into the engine from the atmosphere, and it's not just pure oxygen getting into your engine, because you know that the atmosphere has nitrogen in it and other things. So all of that gets sucked into the engine, but we'll just focus on the oxygen. And then it's hot inside the engine. There's a spark plug. There's fire in there. So boom, it's hot. Everything breaks apart, just like I showed you before. Now they find new dance partners. And now I have just made my CO2 and my two waters. Now they have to go somewhere. Now, by the way, when those got formed, energy was produced, and that drives the engine. That will become more apparent in the second unit. Anyway, now we have to get rid of these molecules, so they have to go out our tailpipe. So they travel down, there's a catalytic converter they go through, there's the muffler, and out the tailpipe. So off they go, out into the atmosphere. Okay, and so you can see that CO2 came out of our tailpipe. It was the form of a gas. And H2O came out of our tailpipe. It's in the form of a gas as well, because the engine was hot, and this came out as a vapor. If you watch closely, though, if you watch a tailpipe, if you're ever parked or stopped at a red light, you look at the car in front of you, drops are coming out of the tailpipe. Some of the water has cooled down and condensed on its way out, and is dropping out as H2O liquid. But anyway, there's our products. So I wanted you to see, if you've never really thought about how the car works before, that's what's going on there. Anyway, we'll stop there.